Welcome to our 7th lesson on electric circuits. We'll be taking a look at energy in our electric circuits today. Now, energy is also seen as work, and the specific symbol that we will be having for energy, which we're going to refer to as work in our electric circuit, will be the symbol W. Note though that sometimes textbooks do refer to a capital letter E. It just means energy, and both of your energy and work actually have got the same unit, and that is a capital letter J for joules. Note though that if you were given kilojoules, you must though be able to convert it to joules, and we'll do so by multiplying with 1,000. Now the symbol was W or capital letter E, but the more common formula that we'll be making use of is the one that says W, which stands for either energy or work, being equal to potential difference times the charge. Now this formula is given to you at the back of your test and exams on the formula sheet, but there is though a few variations to this formula that can also occur. Now before we take a look at those variations, you would have noted that when we spoke about power, I did briefly refer you back again to the formula of power that also talked about work or energy divided by time. Now this formula will come back again in our next lesson when we're going to take a look at cost calculations of power. But for now we will only be focusing on work or energy being equal to potential difference times charge. Now let's see how we can go and break down this formula even further. As mentioned, Q stands for charge, and we do use the unit capital letter C for coulombs. Now you are familiar with V, that stands for potential difference, and in the very beginning of our lessons we did refer that charge is also equal to current times time. So let's in this case assume that we will be keeping the potential difference constant. That means our potential difference we'll still have, but we might not have our charge, which we'll though be able to calculate using current times time. So we will be replacing charge with current times time, and that will then end up giving us a new expression for the work or energy being potential difference times current times time. Now let's continue with this newfound formula. We can now go and decide to replace the V here as well, and we do know that our potential difference is equal to current times resistance. So should I decide to go and replace my V, or my potential difference will end up then with current times resistance, and then the remaining part of the formula, which is again times current times time. Now this will further on be simplified by current squared times resistance times time. So this is once again another expression that we can be making use of for our work or our energy. Now going back again to the previous formula, let's see if we can also go and break it down even further. Keeping the fact that we've now got the potential difference and the time, let's go and see if we can replace current with something else. We do know that current is equal to potential difference divided by resistance. So we're going to be replacing my current though in this formula then with potential difference divided by resistance times then the time, which is the remaining part of the formula. Now this ends up being potential difference squared divided by the resistance times the time. Now many of these formulas could have actually also had power in them, and you will see when we get to our next lesson talking about the costs, this is then where it comes from. We've got now an expression that talks about work or energy being equal to V squared divided by R times time. If you can remember in our previous lessons on power, we said that power can also be potential difference times current, but should I not have the current, I can also replace it with potential difference divided by resistance, which ends up giving me potential difference squared divided by R. So this means our expression that we've got here could have also have been power. So power times time would have been equal to the work. So it would have been the case here. Remember still, power is equal to my potential difference times current. If I would like to go and replace my potential difference with current times resistance, then we'll end up with current squared times the resistance. And once again, if we then thus replace this part of the expression, which is current squared times the resistance that does replace power, we'll once again end up with work or energy being equal to power times time. Now let's go and apply our knowledge to an example. We need to go and calculate the energy dissipated in the 6 ohm resistor in 3 minutes. Now we've been given the total potential difference of the circuit to be 12 volts. You would have noted that this small r stands for internal resistance, which you should not worry too much about. You'll do that in detail next year. And that you've got the total current that will be running through the circuit as 1,2 amp. Now here's my 2 resistors. They want us then to go and determine what will be the energy running through our 6 ohm resistor in 3 minutes. Now it's best to go and take a look at what values do you have. We want to go and calculate energy, which is going to be seen as W. We do have the resistance, that's 6 ohms, and the 3 minutes will obviously indicate to us the time. Just note though that time is usually measured in seconds. So when we get to our calculation, we'll need to make sure that we first convert our minutes to seconds. And something else that we've got is the current. The potential difference though given is only across the battery. And we thus do not know what will be the potential difference across the 6 ohm resistor. We do know though that the whole 1.2 amp of current will be running through this series resistor. Now making use of what we've got, W, R, I and T, we'll realize that the formula that we can go and make use of will be W equal to current squared times resistance times time. Now let's go and fill in the values that we do have. We note that the current will be squared, but it will be 1,2 squared. They only ask for the energy through the 6 ohm resistor, so therefore we'll only go and take a look at all of the energy through the 6 ohm resistor, and we would thus exclude the 3,6 ohm that was given to us as well. As mentioned previously, our time was given as 3 minutes, but we would need to convert our minutes to seconds, and we'll do so by multiplying with 60. So we're going to take the 3 minutes, multiply by 60 in order to get to seconds, and this then will give us 180 seconds. Now multiplying all of this is going to give us a value of 1,555,2 joules when we round it off to 2 decimal places. And do note that the unit for it is a capital letter J for joules.